Okay, I think mics are hot. I hope so. Cool, cool. Hello everyone. Welcome to the OneClass channel. My name is Millan and I am a software engineering student at Carleton University in Ottawa, Canada. Today, I will be going over some commonly asked physics questions at both the high school and university level or college level. If you need some help with your homework or if you're interested in tutoring, check out the links in the description below. Cool. So I'm gonna switch over my screen real fast, and then we can see all the physics. Cool. So let's get down to business. Let's get down to business with the physics with quickness, and let's do it with legitness. You get it? Cool. So the first question that we got today is convert 1 electron volt. Electron volts convert to joules. I'm going to assume that's supposed to be a capital J because joules is with a capital J for that unit. Okay, so first, before we do that conversion, let's think about what a joule, what a volt is. The units for volt is joules per coulomb, meaning it is energy per charge. And we're just trying to get this into joules, which is just energy. So to convert electron volts to joules, it would make sense that, hey, what if we multiply, or this is just voltage. So if the voltage units is volts, which is equal to joules per coulomb. Now it would stand to reason, if we want to convert this to just joules, well, we're going to need to multiply something that would, if we want to multiply it so that there's a coulomb on top, so that we can cancel the coulomb on the bottom of the unit. Okay, so what charge should we use? Well, we look at the name, electron volt, electron, that's a nice hint. So why don't we multiply one volt, multiply that by the charge of an electron. That should just give us a joule left, and that will be how many electron volts are in a joule. Okay, so I know the charge of an electron. And let's just do the absolute value because electrons do have negative charge, but let's keep our numbers positive for now because it'll be easier to help visualize the stuff. The charge of an electron is 1.6 times 10 to the negative 19 coulombs. The C stands for coulombs, named after the scientist, the Coulomb guy. Yeah, he was probably a smart guy. Okay, so if we multiply this by 1 joule per coulomb, well, you see how the coulomb on the downstairs here, that coulomb neutralizes the coulomb up there on the units. Whoa. Whoops. Okay, so the only unit left here would be joules. So we know that 1 electron volt is 1.6 times 10 to the negative 19 joules. Now, let's say we want to go the other direction. Or I'll write this out like value of 1 EV. EV means electron volt. Okay, so if you want to go the other way, so like let's say you're given something in electron volts. So let's say you have like 1, or let's say you have like 3 electron volts. If we want to convert that convert EV to joules, well, we know there's going to be this many joules, 1.6 times 10 to the negative 19. That's how many joules are in 1 electron volt. So you multiply it like this, 1.6 times 10 to the negative 19 joules. And we know that that's how many joules are in 1 electron volt. 1 electron volt. So we do the math here. You see the EV up here and down here, they neutralize each other. So all that's left is joules, which is just 3 times 1.6, and that's going to be 4.8. Yeah, 4.8 times 10 to the negative 19 joules is equal to 3 electron volts. Okay, so got to be very comfortable and familiar with this stuff. Yeah, and canceling out units and all that. And if we wanted to go the other direction, like if we want joules and we want to go from joules into electron volts, say we have 100 joules. Well, to convert joules to EV, electron volts, we would just divide by the fraction that we got above. So we know that we have 1 electron volt per 1.6 times 10 to the negative 19 joules. The joules on here neutralizes the joules up there. And the result of this, well, pulling out the handy dandy calculator to find out. 100 divide 1.6 times 10 to the power of negative 19. And the result of that is 6.25 times 10 to the 20. That's a big number, electron volts. And that makes sense because electron volts are significantly smaller than 1 joule. So, yeah, that would make sense to get a massive number for 100 joules. Okay, so, yeah, I guess to be more precise, you could use 1.602, but typically 1.6 is good. Okay, and I guess the junior tutor here went a little bit deeper, and I guess they showed like some applications of where this would be used in like an electric field, because that's where really the unit joules per coulomb comes from. It's like how much energy is a single piece of charge gonna have. Yeah, so yeah, the above solution is good. Above solution is good. Perhaps. Yeah, let's just say it's good. Okay, cool. Good job. The next question that we got on the menu today is about capacitance, and it's asking about the formula and units. It's kind of a open-ended question, but let's rewind for a second. Capacitance only exists when we have capacitors. Capacitors. Now, let's think about the word capacitors for a second. It kind of has the same type of word structure, or a subword that we can find in here is like capacity, storage. These are kind of like just clues of what a capacitor means just by looking at the word itself. Like it's got capacity, capacitor. What does it store? Well, it stores charge. Stores charge. Now, what do capacitors look like? Well, suppose we have an electric circuit like this. Maybe we got like a voltage source. We can call that V, voltage source. And capacitors look like this. And they literally look like this because they are like two parallel plates that are not quite touching. So imagine that these two calculators are like the parallel plates. They're very close together, and when you have a voltage across them, there will be some charge that accumulates on the individual plates. Let's say blue calculator is the positive terminal and purple is the negative terminal. There would be like a bunch of positive charges that are accumulating here and negative charges accumulating here, and there's going to be like a potential difference between those capacitors. Okay, so maybe if we had like positive charges accumulating there, negative charges accumulating here, and across those plates we're going to have a voltage like this. So that could be like V capacitor. Okay, now how will we find the capacitance formula? Okay, so what the capacitance is like this is a property of a capacitor. A capacitor. It's similar to how, like, you know, a resistance and a resistor. Well, the resistance is just the property of that particular resistor. So, the units for capacitance, units are farads. And that's named after Michael Faraday, who is a very clever scientist a long time ago. And he's also behind Faraday's law. So, you know, if you have a law and a unit named after you, you're probably pretty good at science. And but you don't write farads, you just write big F. And you know, it might be tempting to say that, hey, that F stands for fun, but it's farads. And most commonly, you'll have millifarads, microfarads, sometimes even nanofarads, but those are going to be the most common prefixes that you'll have, because like if you have like 5 farads, that's a massive capacitance. So it's typically going to be small values like this. Okay, now how would you find it? Well, when I search up capacitor equations, we can see that that's not the one I want to start with. The one I wanted to start with is, if we only know like the capacitor and we don't know what it's acting like in a circuit, we can figure out the capacitance. How this is calculated is epsilon times A over D. Okay, this I'll explain what some of these things mean. C, that's the capacitance. Epsilon naught is the permittivity of what's in between them. Of material between plates. This, like in general, should be given to you by the question. Yeah, so for example, like sometimes you might just have nothing between, or not nothing, you might just have air between your parallel plates, and that would have a certain epsilon naught value. You might also have maybe like a piece of dielectric, maybe like a piece of plastic, something like that, between the parallel plates, and that will have a different permittivity. It's basically saying like how easily is like how well the material between them is able to store an electric field. Okay, but this will generally be given to you by the question. A is the area of the plate. And D, this is the separation of the plates, or distance between plates. So if we draw it more in like a 3D sense, like we got some square plates, this could be plate 1, and like maybe all the way back here we'll have like a plate 2 going here. So the distance like that between them, that's D. like that. This would be the area, or maybe better to like draw it like that. I'll reset first drawing. Okay, the separation is D. The area, the cross-sectional area is A, and there's gonna be like some type of thing between here. Maybe something like, whoops, not purple. That's a kind of dark. Let's maybe put a lighter color, like light sky blue. In between them, there's gonna be something, and that's gonna have a property of epsilon naught, which is just permittivity. Okay. And another equation that we can use to look into the capacitor, or one of the like important capacitor values, is the amount of voltage across the capacitor is proportional to the amount of charge that accumulates on the capacitor. And they're related through this equation. Q equals CV. This is voltage across capacitor. This is the capacitance. And Q is equal to charge on capacitor. Okay. Yeah, and this could be another equation that you could use to that involves capacitance, and as well, this is going to give you more insight on the inner workings of the circuit with the capacitor inside. Now, if we wanted to take the time derivative of this, so if we did like d over dt of q equals d over dt of cv, c is constant. We know that the time derivative of charge is going to be current. So that's going to be I equals C. We can move that outside because it's a constant, and it'll be the time derivative of the voltage. Whoops, not dV. It's a d over dt of the voltage. And this is another way that you could get meaning from knowing the capacitance, or if you want to solve the capacitance, if you know how the voltage is changing and you know the current going through it, this can help you solve for the capacitance. Okay, so yeah, hopefully this helps address the question. The unit's farads, named after Faraday, and there are multiple different ways or multiple different equations that involve a capacitor's capacitance. So yeah, fun stuff like this. So the above solution is good. Is good. And question should be more specific in how capacitance values are expected to be used. Okay, cool. Okay, so the next question that we got on the menu today is, it's asking about the visible light spectrum, and we're gonna look for some definitions, wavelengths, and then we're also gonna talk about what makes things different color. Like, I'm wearing a blue shirt right now. My walls are painted orange. There's red on the Canada flag behind me. Like, why do different colors even exist? That's kind of the question of the day, or question of the hour. Okay, so for the visible light spectrum, a visible light spectrum is visible light spectrum. This is a portion of the electromagnetic uh, electromagnetic wave spectrum. So suppose we have the electromagnetic wave spectrum here. Here we have a low frequency. Whoops. A low frequency, and here we have high frequency. High frequency. So low frequency, we're going to look more like this. And high frequency, well, it's going to be a little bit more frequent. Okay. The visible light spectrum is only a subset of it. And lower frequency or higher wavelength, those are the same thing. High wavelength. And this is low wavelength. Lambda is wavelength. Yeah, and we'll see that more in the equations. But if we have lower frequencies than visible light, this becomes like infrared. And like maybe even into like radio waves. And this is all invisible. And over here, it's invisible as well. Invisible to human eyes, that is. Some animals have infrared vision, and they can. That's why some animals are better able to see in the dark, because their eyes can pick up more infrared stuff. And infrared waves also are what powers like night vision goggles. So if you're trying to see in the dark, there's no visible light, but there still is a lot of infrared light that is around. And night vision goggles just transform, or it interprets those infrared signals and transforms them into visible signals so that we can better see in the dark. So yeah, that's just one application of infrared lights, is in night vision goggles. And yeah, in the invisible for higher frequencies, this is getting into like ultraviolet light, and then it also gets into like X-rays and gamma rays, and that tends to be higher frequency stuff. Okay, now within the visible light spectrum, we have our different colors, and this is difficult to draw. It's better if I look into something like this, a nice diagram that shows the visible light spectrum. Okay, courtesy of ThoughtCo. Thanks, ThoughtCo. Really thoughtful of you. So you can see, hey, it really does follow like a rainbow type of way. So if I'm gonna draw it out, like we got like red, orange, yellow, green, like blue, purple, violet. So you can kind of see why like infrared, and here is like ultraviolet. You can kind of see like they get their names based on which light they are the closest to. Like you go more towards the red direction, you'll get infrared. More towards the violet direction, you'll get ultraviolet. Okay, and then the wavelengths that these occupy is going to be like this border right here, where you can pretty much see is around 740 nanometers. And here is or for wavelength. Here wavelength is equal to about 380 nanometers. Now this is going to be different for different people. Like some people have certain degrees of color blindness where they're not necessarily going to be able to see certain colors. That's because the cone cells in your eyes are the ones that differentiate the wavelength of light that comes in, and some people have some people do not have the same ability or the same number of cone cells in their eyes that allow them to like differentiate different colors. Different animals as well. So for example, dogs don't really see colors as well as humans. It's more So they would have like a more narrow visible light spectrum for a dog eyes. Like these are for human eyes. But other animals, like I'm pretty sure butterflies, they're able to interpret electromagnetic information in a higher visible light spectrum from us. So they would see more infrared and more ultraviolet stuff if you were a butterfly. So yeah, and let's say if you want to know the relationship between wavelength and frequency, it's as follows. So wavelength is equal to velocity of the wave, meters per sec, divided by frequency. Or yeah, and another way that we could write this is frequency equals velocity of the wavelength. So lambda, this is wavelength, f is just frequency, and v is velocity of wave. In this case, it is c, which is equal to 3 times 10 to the 8 meters per second. Okay, so that is some fun stuff about infrared or visible light on the visible spectrum. And colors is just like different wavelengths will have different colors. So you change your wavelength. If you gradually reduce your wavelength as you start at red, you will see that you will fly through a rainbow and maybe find a pot of gold at the end of it. Who knows? Yeah. Fun stuff. Visible light. I see. Yeah, the above solution is good. Okay. The next question that we got on the menu today is asking for the laws of inertia, definition and formula. So the law of inertia kind of comes from our good old friend Isaac Newton and Newton's first law. Was this the first law that Newton never followed? Yes. But probably wasn't the first law that he ever wrote, but it was the first one that he ever followed. He followed it before he wrote it, believe it or not. Yeah. So what Newton's first law basically is, it states that objects at rest tend to stay at rest. Tend to stay at rest. Objects in motion tend to stay in motion. The only way to change the motion of something is with a force. You can only change motion of objects with forces. And inertia is how much something is affected by a force. Is how much something is affected by forces. Okay, so let's say we have a gust of wind. Sometimes there are windy days, and we can feel that the wind does apply a force, right? The motion of the air itself, it does apply a force. Ask any flag or any wind turbine, they'll tell you wind definitely has a force. But think about how things respond to that force of the wind. if we have like, a flag waving in the air, the wind is going to affect the motion of the flag a lot. Lots of wind, well, lots of flag motion. But you think about something like a brick. A brick, you can have a lot of wind that goes onto a brick and it's not really going to move. It has a lot more inertia. So another way that we can kind of say inertia is mass. Inertia are tightly related. Okay, so like in the example that we just had with wind, wind would be like a constant force. It would always be the same, but the way that different things respond to it, well, heavier things are going to be more resistant to the impact of wind, and lighter things with less inertia, things with less mass, things that weigh less, are going to be more affected by a force like a wind. Okay, so yeah, and it also kind of goes into Newton's second law, which is like the magnitude of the acceleration, because a force always causes acceleration. So Newton's second law. Pretty much Newton's second law is force equals mass times acceleration. So that's force. This is mass slash inertia. A is acceleration. Well, for this to be true, like more with a constant force, more mass means it has to have less acceleration. Less acceleration means, well, the motion is not going to change as much. The acceleration is what defines how the motion of the object is going to be. Okay, so is there necessarily an easy formula that's all, or a lot of, anytime you see inertia, you should kind of be thinking about mass, because they are very tightly related, and all equations and laws that are involved with mass are also kind of de facto related to inertia as well, because of the mass and inertia relationship. Okay. So, yeah. Another way that you can kind of keep this in your mind is like inertia. You think about the word inert, like not trying to move. So more inertia, I'm more inert. I'm trying to move less and less. Or it's not necessarily just things at rest as well. Like, would you rather consider trying to stop or trying to slow down someone riding a bicycle versus a train? Like, a train has a lot more inertia because it has a lot more mass. You trying to apply just the force of your push on a train, well, you're probably not going to slow it down at all. You're probably just going to have a very bad day if you try to slow down a train by pushing on it. But for someone like a bicycle rider, with the force of an arm push, you can cause a significant amount of deceleration, because a bike rider has a lot less inertia than a freight train. So it also works not just for like getting things from rest to start moving. It could be like anything that's moving and trying to change the properties of how they're moving, whether it's slowing down or changing directions. All easier when there's less inertia. So the above solution is good, but yeah. Okay. The next question that we got on the menu today is asking, what is Hooke's law and the spring constant equation? So Hooke, that was a scientist. That was pretty smart way back in the day. And Hooke's law is basically all about springs. Spring. Yeah, we're talking about spring and it's not even winter. Yeah, okay. Springs, like, not the season, but like these things. If you got any mechanical pencils, they probably got springs inside. If you ever got a pogo stick, you know, there's definitely going to be a spring in there. And we know that if you push on a spring, if you compress a spring, if you, like, try this at home. If you got a mechanical pencil, if you try to push it down, well, the spring is trying to resist the amount of, it's trying to resist against you. It's pushing back on you when you push down on a spring. So, Hooke's law basically states that the force that a spring applies is proportional to its stretch or compression. Yeah, it is directly proportional to its stretch or compression. Its compression, well, if you push down on a string, they're going to push back. And for stretch, well, you ever been to like a pinball machine and like you pull out the little pinball ball pusher and it like instantly springs back in and launches a ball up there? That's an example of a spring that is stretched out and how that will also apply a force. Okay. Now, Hooke's law is true within the elastic limit. Of course, like if you really, really stretch out a string, you're going to irreversibly damage it. And of course, Hooke's law is not going to be true in that case. So Hooke's law is true in the elastic limit. The elastic limit is where you're starting to damage the spring and it's not going to act the same way. So Hooke's law is valid in the elastic limit. The elastic limit. And instead of just saying proportional, it's linearly proportional. Okay, so the equation is F equals Kx. F, that's the force. Let's say Fs because this is for a spring. So force of spring. Whoa, let's bring it back. K, that's the spring constant. A high K value translates to a stronger spring, and low K values translate to weaker springs. So the suspension in your car, that's a pretty strong spring that's going to have a higher K value than the spring in your mechanical pencil, which probably has a very low K value. Okay, and X, this is the distance that the spring is compressed or stretched. Okay, so let's actually draw out an example. Suppose we have a wall here and we got a spring and it's actually a pinball machine and we're trying to pull out the plunger. I think that might be what it's called. And you know, let the ball fly back. Okay, so this is the start, and then we stretch out the spring like this. And the amount that it's stretched out, X, is going to be, you know, it's just going to be X. You don't necessarily need to give a number just to show like an example of this in progress. Let's make the plunger ball black so it's a little bit more clear. And we know that, well, you know, the farther you stretch it back, the more of a force it's going to apply. Now, which direction is the force? The force is always towards the center line or towards the natural position of the spring. So in this case, F of S, Fs would be this direction. Now, if we were to compress the spring, maybe looking something like this. We would see that this distance is going to be, oh, let's call this x1 and call this x2. And we can see here that the force would be this way. Fs, trying to return to its unstretched out natural spring position. Okay, so sometimes you'll write the Hooke's law as a negative kx or positive kx. Like, it's very confusing how sometimes you can see it written either way, but just know, like, it's good to draw out a diagram and then you can kind of know, because it depends on as well how you define your directions. So if we say forces towards the right are positive, you know, we'd want to set up our arrows. You basically just want to look at the diagram more than you look at the signs. The signs should agree with your diagram. Make your diagram before you make your signs, not the other way around, because your diagram will be more powerful, or in terms of, it's going to be more powerful in terms of telling you what's going on, because your equations only make sense with respect to the diagram. So make the diagram first. And yeah, the above solution is good. Is good. Diagrams would help. Be helpful. Okay. Took a nice sip of water, and now we can talk about water. So the question that we got right now, next question on the menu, is what is the index of what is the speed of light in water when we know that the index of refraction is 4/3? Okay, so the index of refraction, that is represented by the Greek letter mu. Mu is equal to 4 divided by 3, and this is equal to the index of refraction of water. Index of refraction of water. Water is my favorite beverage. Fun fact about me. Yeah. Okay, so this is just a property like of the material. Let's say if we were doing like you know, what is the speed of light inside of, I don't know, oil, we would have a different index of refraction. Or if we did glass, or I don't know, something like acrylic, we would all have different mu values of that. So yeah, this is just a property of the material. And we are looking for the speed of light in water. So we can set up our equation like this. The equation is v, the velocity of light in material, is equal to the velocity of light in a vacuum. In a vacuum meaning like, you know, going through no material. So this would be like a sun ray deep in space. In deep space, it's literally a vacuum. There's nothing there. So how fast light travels through there is our baseline. Then we're going to divide it by the index of refraction of material. Okay, this whole thing, actually I'll just copy it over. Technology, super cool. This is equal to C, because it's used so frequently, which is equal to 3 times 10 to the power of positive 8 meters per second. Okay, and we know what the mu is, which is the index of refraction of water. So let's just put these puzzle pieces together and get the number. So V material, we can just write it as V because we know exactly what it is going to be C, which is 3 times 10 to the 8 meters per second. multiply, or instead of doing divide by mu, we can do multiplied by the inverse. So we can multiply it by 4 over 3 to the power of -1. Just writing it this way could be a little bit easier to put it into your calculator, because some calculators are unfriendly to dividing by divisions. So yeah, I'll send that through my calculator real fast and we'll see what we get. So 3 times 10 to the power of 8. And to multiply by that, we could just like flip it upside down. So it's could be like multiplied by 3 divided by 4 times 3 divide 4. And the result I got was V equals 225,000 meters per second. And I think that translates to 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5, 6, 7, 8. Okay, I guess my counting is just wrong. So this is just equal to 2.25 times 10 to the 8 meters per second. 904. Yeah, and that kind of makes sense, because really just like 3/4 of 3. It should be 2.25. And yeah, that's precisely what we got. So yeah, math checks out. So the rough solution is good. Awesome. Okay, so the next question that we got on the menu today is about the human body and the way the blood moves through the human body. Okay, so the question is asking, blood is flowing through an artery of radius 2 millimeters at a rate of 40 centimeters per second. Determine the flow rate and the volume that passes through the artery in a period of 30 seconds. Okay, so let's identify the numbers of interest out of this question, because all this other stuff, you know, to contextualize it inside a human body is not necessary. We're just trying to get the numbers, get the proper calculations, and then get our final answer. And then once we get our final answer, recontextualize that in terms of what's going on in the question originally. Okay, so we got blood flowing through the artery, radius of 2 meters. So radius is 2 millimeters, and this is the it's kind of like the opening that the thing is flowing through. Opening that fluid is flowing through. Okay, now blood is flowing at a rate of 40 centimeters per second. Yeah, so I guess linear flow rate, let's call that I guess they had it as V. We can keep it as that. V is equal to 40 centimeters centimeters per second, and this is like linear flow rate. And let's convert these SI prefixes into coefficients, just so our units will always line up. So this will be 2 times 10 to the -3 meters, and V will be 40 times 10 to the -2 meters per second. Okay, so we want the volumetric flow rate. Volumetric flow rate as well as total or volume flowed. I guess that's probably the best way to describe it. The volume flowed in 30 seconds. In 30 seconds. Okay, so let's get the volumetric flow rate. So we're given the radius of the opening and the linear velocity, which is like the length of stuff that goes through, but we need to just get the volumetric stuff, we have to multiply that by the area of the opening that is flowing through. And we're going to assume that the flow rate is always constant. Yeah, because I guess in the human body, because your heart is like bum 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 bum, like it sends a flow and like in pulses, like it's not always going to be 40, it's going to like vary around. But for the purposes of this question, we can just assume that the heart is more like a constant pump that doesn't like fluctuate the flow rate. Yeah, and that's a nice approximation that we can use. So we want our volumetric flow rate. I wonder what they use for the variable here. They used Q for volumetric flow rate. Capital Q. So we can use the same. The variable that you use is not particularly important. What's important is that you you keep it aligned in your head. You're like, don't all of a sudden think that Q now means charge. Okay, so we know that our volumetric flow rate is going to be equal to the area of our opening multiplied by the linear flow rate. Area of opening, and this is linear flow rate. Okay, now it says it has a radius of 2 millimeters, so we can only really assume that it's going to be like perfectly circular, because otherwise it would be impossible to calculate the area without additional information. So it has to be a circle if we're only given the radius. So the area of a circle is going to be equals pi r squared multiplied by the linear flow rate. And let's sub in the numbers. So we know that our R value is 2 millimeters. So that's 2 times 10 to the negative 3 meters squared. Multiply that by the linear flow rate, which is 40 times 10 to the negative 2 meters per second. Okay, now if we look at our units, you can see that we have meters squared times meters per second. So our final unit is going to be meters cubed per second, which is perfect. That's the volumetric flow rate, the amount of volume. That's the meters cubed per second. Okay, that's great. And for the value of this, let's send it through the calculator and figure it out. So we got pi multiplied by, and then in brackets, 2 times 10 to the power of negative 3 meters. But we got to square that whole thing. Square it. And then multiply by 40. Multiply by 10 to the power of negative 2 for the centimeters. And what do we get from that? We get 5.0265 times 10 to the negative 6, and all of our units, we converted them into base SI, so it should be meters cubed or cubic meters per second. And that is a very small number, but also keep in mind a cubic meter is quite massive. Like so we would expect a very small number of cubic meters. A cubic meter, that's like you could fit probably 1 or 2 people inside of a cubic meter. 1 or 2 small people. Okay, so this will be our volumetric flow rate. It will be that value. Is that the same that they calculated? 5.0265. I guess without the rounding, it's good. Now, if we multiply the total volume flowed in 30 seconds, well, we just multiply our volumetric flow rate with the time. So I guess the volume, oops, let's not use that curly V, let's use capital V for volume, or let's just say vol of blood is going to be Q multiplied by the time flowed, QT. Ain't that a cute little thing? What a cutie. Ha ha ha. Okay, so to do the math, let's do 5.0265 times 10 to the negative 6 meters cubed per second. You know, this is kind of like asking, if you're driving 70 miles per hour, how long, and you drive for 1 hour, how far do you go? 70, buddy. So it's kind of like that. So we multiply this by, how long does it ask for? 30 seconds. So if every second we're flowing this much, multiply that by 30 to get how much we'll get in 30 seconds. So 30 seconds. So pull out the calculator. Still got the old value of 5.026 times 10 to the negative 6. Okay, multiply that by 30. And what do we get? Our total volume is 1.508. I'm rounding up because it's actually 1.5079, but I'm going to round up to 508, multiplied by 10 to the negative 4 meters cubic meters, actually not per seconds anymore, because the seconds down here and the seconds up here neutralize each other, so they got to be just cubic meters, and that's still a very small amount of cubic meters, but considering how massive a cubic meter is, that makes a lot of sense, that you'll still have a small number after going for 30 seconds. Okay, and hopefully we got the same calculation here, 1.507. We'd accept that because it's likely just a rounding error with the calculator, but otherwise the above solution is good. So the key thing that you want to pay attention to is the units. The units can tell you a lot about what you should expect in the question. Okay. Okay. The next question that we got on the menu today is asking, what type of materials are permanent magnets made of? And we have 4 multiple choice options. So this kind of like narrows down what our possible actions are going to be. Okay, now, we can make an easy disqualification first. Keyword, magnets. Well, most likely it's going to be from one of these options that has magnets in it. So we can disqualify dielectric materials. Oops, let's write that out. Dielectric materials. No relation to magnetism. Okay, I'll write this as disqualified. So this has no relation to magnets, and where dielectric materials are used is in capacitors, in the material between the plates of a capacitor. So these are used in capacitors. No cap. Alright, aye, Captain Capacitor. You're not Captain Capacitor, dielectric materials, that's not going to be an option. And then we have our other options left. Paramagnetic, diamagnetic, and ferromagnetic. Okay, so this can be a little bit easier if you speak French, because en français, as well as in Latin, that's where it comes from originally. Iron is just, got ahead of myself here. So en français, fer equals iron. If you ever seen a periodic table, you would see like Fe is the element for iron. It means fer. It comes from Latin, but since not that many Latin speakers, si tu peux parler en français, tu vas savoir que c'est de fer. And we know that iron is magnetic. So The answer here is that it's ferromagnetic materials. And the key word that you want to look for is fair. And we know that like iron is fair, and fair is magnetic on its own. So iron makes permanent magnets. Okay. And the reason why it makes permanent magnets is because of the fact that they have unpaired electrons in their D shell. And those unpaired electrons, they can be set up in a way that, they're all aligned. And that is what causes the magnetic force to exist, which is what makes a permanent magnet magnetic. Okay, so here I have a nice illustration of how things might look, like on an atomic scale. Like these arrows would represent like unpaired electrons and the direction of their spin. That really gets deeper into chemistry. But you can see like paramagnetic. That would be stuff like, trying to think. Like aluminum, and metals like that are not magnetic on their own, but they are magnetic when you apply an electric field to them. And I guess diamagnetic, we have like no unpaired electrons, and yeah. So we know that we got ferromagnetic materials, and keyword that you want to look for is fair, iron. French people rejoice that French is useful for giving you clues in multiple choice questions like this. Okay. So, yeah, the above solution is good. Okay, so the next question that we got on the menu is asking us exactly this. A crate of mass 32 kilograms is riding on the bed of a truck attached by a cord, looking like this. And that truck is driving fast. There's no friction, so we got to find the maximum acceleration that the truck can have before the cord breaks. And the maximum amount of tension in the cord is going to be 68 newtons. As soon as we get to 68 newtons, that one cord is going to turn into two cords that are not as long as they are originally. That's what's going to happen once we reach 68 newtons. So let's draw a free body diagram for this situation. Okay, so suppose we have a truck. This can be like the back of the truck. There's our wheel holes. This can be like a dude driving. And then we have our mass here, 32 kilogram. Okay, and we're going to have a cable here. So the max that this can have is 68 Newton. And are there any other forces that are in this system? Yes. Yes, there are. So we know that, assuming this is on Earth, we're going to have a gravity force, Fg, and the back of the truck is going to have an opposing force, the normal force. And they will perfectly cancel each other out because the net force will be zero vertically. Vertically, the net force is zero, and because, well, we know that there's no vertical acceleration, we're only accelerating horizontally as the truck accelerates. Okay, so because there's no friction, when this truck slides, or when this truck starts to drive, this mass doesn't know that it's moving. Like, it doesn't know that it's moving until the cord starts pulling on it. But since there's no friction, like I don't know if you ever tried this. Like, if you ever had a wagon with something on it, and then you pull the wagon real fast, and the thing on it slides off. Or if you ever seen those magicians who put things on a tablecloth and they pull away the tablecloth and the stuff stays there, that's essentially what would happen here if the truck just started to accelerate, because there's no friction. Okay, so we know that F equals ma. The only unbalanced force that would cause the mass to move, because it's connected via the cable, is Fc. So let's call that F cable. Fc for F cable, the force of the cable. And the force of the cable has a maximum force in it of 68, because once it gets past the 68, well, it's a split. That mass is sliding off, probably going to hit someone on the highway. Not a great thing. So Fc is equal to mass times acceleration. The only mass that is involved in here is the mass that's given there, the 32 kilograms. So, and we're trying to solve for the maximum acceleration. So A equals Fc over m. And Fc, well, that should be the maximum, because we're trying to find what is the maximum acceleration that we're not allowed to pass. So the moment that it hits 68 newtons, we'll have 68 newtons with a mass of 32 kilogram. The acceleration at that time is going to be 68 divided by 22. Pull out the handy calculator. 68 divide 32. 2.125 meters per second squared. So meters per second squared. So if the truck is suddenly going at like 2.5 meters per second squared acceleration, well, that cable is going to be like, yo, chill out, bro, chill out. That is too far. I'm actually going to brake. If you had more than that for acceleration, it's going to brake, and the thing's going to slide off the truck, and probably get you in trouble. Okay, so we know that the maximum acceleration, we don't pass 2.125. If you pass that, you're going to have some car insurance stuff to deal with, and that's not going to be great. Okay, so yeah. And then we used Newton's second law, just like them. And 2.1, well, yeah, sounds about right. I guess you could, since the question gave us everything with two significant figures, we should round that to two sig figs. 2 SF, two significant figures, not San Francisco, but San Francisco's a nice place. This would just be 2.1 meters per second squared. Okay, just for significant figure adjustments. Cool. And yeah, the above solution is good. Okay, so the next question that we got on the menu today is, how do we calculate the momentum of a photon? Okay, so the short answer is that it is really just this equation. The momentum P is equal to h divided by wavelength, where P is the momentum, h is Planck's constant, which is 6.626 times 10 to the negative 34 joule, I think it's joule seconds. I'm going to search that up real quick. What's Planck's constant? Planck constant. Meter squared per kilogram per second. That's the same as joule seconds. And here, this is a wavelength. Okay, this is the real equation that you want to use, but I'll show you how we got to this place in the first place. Or we got to this point in the first place. Okay, so a long time ago, there was a dude named Einstein who made this moderately famous equation. E equals energy is equal to the mass multiplied by the velocity of light squared. This is mass energy equivalence. Thanks Einstein for figuring that out. It's a pretty cool equation. So this is Einstein mass energy equivalence. And then we have momentum of a particle, which is just P equals mass times velocity. Okay, if we were to isolate mass out of here, we would have mass equals energy over c squared. Sub that into here for mass. The momentum is equal to the energy that it has divided by c squared, which is the speed of light, divided by, or multiply that by the velocity of the particle. But since v is equal to c, we can simplify this to do that. So we will just have E over C. Okay. Yeah, and now the energy of a photon is given by E equals Planck's constant h multiplied by the frequency. Now here they use V. All my life I've been taught to use F for frequency, but I've seen some people, like more often than I'm really comfortable with, using V for frequency. I guess that works, but in my opinion, F makes a lot more sense because you don't use F for other things like velocity. So that's just my opinion. Yeah. Okay. So we can sub out HF for the E in here. So P equals HF over C. And then we know from our universal wave equation that velocity is equal to frequency times wavelength. And if we wanted to just get the wavelength, or just get the frequency, because we're trying to sub out that F to be with respect to the frequency, it's going to be V over lambda is equal to, V over lambda is equal to F. Stick that into here. P equals H V over lambda C, but we know that since C is equal to V, we just get P equals H, Planck's constant, over the wavelength. Okay, so that's how we get the momentum of a photon, just by knowing its wavelength. Okay, so you can see where that equation comes from. We combined a lot of different ideas: mass energy equivalence, momentum of a particle, energy of a photon, and the universal wave equation. Put all those puzzle pieces together, and then we can get here momentum of a photon given the wavelength. Yeah, spelling. Okay, so yeah, that's exactly how we came across this. Okay, so yeah, above solution is good. However, using F to represent frequency would be better, as the V used can be confused with velocity or voltage. Okay, groovy. Super cool. Momentum. Okay, next example that we got is how do we define average speed with an example. So average speed is defined as followed. It is the change in position divided by the change in time. So if I change my position by 100 kilometers in 1 hour, well, I would have an average speed of 100 kilometers per hour. If I actually don't move at all, and I basically just sit in my chair, not moving at all for 10 years, well, I'm going to have a 0 meters per second velocity, or average speed, because, well, I didn't move. So this is how we define it. We look at the change in position and divide that by the change in time. Okay, so let's actually run this through with an example. Yeah, I guess what they have here is the example that they have here is it's also dependent on what is already known. So if you only know positions, so let's say when time is equal to 1 second, my x position is equal to 5 meters, and when time is equal to 20 seconds, my x position, I finished a 100 meter race. So x equals 100 meters, and I got a head start, or maybe at time equals 0, I was at the starting line, and 1 second deep, I was 5 meters in. 20 seconds later, I finished the race. It's pretty slow. I think I could do that faster in real life, but just for the sake of the question. So the change in position is going to be, let's actually give it a t1 x1, t2 x2. So it's going to be like x2 minus x1. That's the change in position divided by the change in time. T2 minus T1 equals 100 meters minus 5 meters divided by 20 seconds minus 1 second. So it would be 95 over 19. 95 divided 19. In this case, I would be a solid 5 meters per second. Okay, that could be an example of how you get the average speed if you're given the positions, only knowing the positions. You don't necessarily have to start at 0, but you could scale it to be at 0 if you incorporate the proper amount of factors and offsets. But if you know the speeds, you would take the average as if you would take like the average position. Like if you'd spent knowing speeds, you would take the average like anything else. So let's say for 5 minutes I was going 10 kilometers per hour. For 10 minutes I was going 100 kilometers per hour. Well, it'd be like you would take the average that way. So we can do that as an example. So x going 5 meters per second for 10 min then 20 meters per second for 1 minute. Average speed would be well, it would be 10 times 5 meters per second plus 20 or it would be 1 plus 1 times 20 meters per second. Divide that by the total of 11 minutes that we were driving. And we would have something like this. So it'd be 50 plus 20 divided by 11. Divide 11. And we get like our average speed is equal to whoops, 70 divided 11 is going to be equal to 6.36 meters per second. Okay, and that makes sense that it's going to be a lot closer to 5 than it is to 20, because we've been going at 5 for legitimately 10 times longer than we've been going at 20 meters per second. Okay, so that would seem like a reasonable answer if for a situation like this, and you're you know, averaging the known speeds already. Yeah. So the above solution is good. Is good. Question is a little vague in stating what is known already before calculating the average speed. Okay, cool. Okay. So the next question with very big text is asking us, we got a 6 kilogram bucket of water being pulled up straight by a string at a constant speed. At a certain point, the speed of the bucket begins to change. Oh, when speed changes, acceleration's going on. Don't forget that. The bucket now has an upward constant acceleration of 3 meters per second squared. What is the tension in the rope now? Okay, so let's extract the numbers of interest from this equation. So we know we have a mass, and that is 6 kilograms. That's a lot of water. Starts at a constant speed, and then at a certain point the acceleration becomes 3 meters per second squared. So acceleration, let's say a upwards arrow, the upwards acceleration, that becomes 3 meters per second squared. Okay, so let's draw a free body diagram. So this could be our bucket, our 6 kilogram bucket, and we know that it's going to be it's going to have a gravitational force Fg, and then it's going to have F cable, the cable that's pulling it up. Okay, so when it's moving at a constant speed, there's no acceleration. Oops. No acceleration. No net force. No net force, meaning that Fc is equal to Fg. Okay, and that's when it's moving up at a constant speed. But what's really interesting is when it starts to accelerate. Okay, so when it accelerates, acceleration, net force is up. And the net force, so let's call that F net. F net divided by mass is equal to the acceleration up. So A up. Okay. So if we go back here, FC not only has to balance out FG, it's also going to have the additional acceleration upwards. Okay, so so that's going to be like the total amount of tension in the cord, because the cord not only has to hold up the weight, it also has to like add the additional force of acceleration. Okay, so FC or FC is going to be the force of the gravitation plus F net. Okay. Yeah. And you could kind of see like the exact way that they set it up here. So we know with Newton's first or Newton's second law that F equals ma. So this is going to be m times the gravitation, the acceleration of gravity, plus the mass multiplied by the acceleration due to the upwards pull. So that will be a up, and we can factor out the mass. So Fc equals mass times gravity plus acceleration upwards, because that's the actual acceleration that the cord needs to supply. It needs to supply an upwards acceleration to counteract the acceleration down due to gravity. So that's why we have the g, as well as the actual acceleration upwards, which is I think it was given as 3 meters per second. Yeah. Okay, so let's sum in the numbers. We had a 6 kilogram bucket of water, and we're going to assume that nothing spilled out and changed the mass. We got 9.8 meters per second squared. That's gravity, and the upwards acceleration is 3 meters per second squared. Meters per second squared. So let's ask our good friend the calculator, what is the numerical answer to that? So 6 multiplied by, in brackets, don't forget the brackets, bed mass, real fast, 9.8 plus 3, in brackets, multiplied by 6, and we get Fc, the force, the amount of tension inside the cable, is 76.8 newtons. Okay, so it's good to have a diagram like this, and it can kind of give you a lot of intuitions about like, what type of forces to expect, because, yeah. So first we have to counteract gravity, and then with the additional acceleration, there's an additional force inside the tension of the cable. And it was calculated precisely the same way, and 76.8. Give ourselves a high five, because that tension is found. Cool, so the above solution is good. Okay, the next question that we got on the menu today is, if you have 10.8 meters per second, I'm going to assume it means if you have 10.8 meters per second, how do you convert that to radians per second? Okay, another assumption we need to make is assume circular motion. Because if I'm traveling 10.8 meters per second in a straight line, how would you get radians per second? How would you get the angular velocity? Well, you can't. I'm not even moving in a circle. You need circular paths for angular velocity. Okay, so a nice equation that you can use is assume circular motion, and we also assume that assume 10.8 meters per second is tangential speed. Tangential speed in circle. So suppose if we draw a circle out like this, and maybe if this is like a real life situation, this is like a roundabout, and you know, you got your little car here and you're driving. Like you'd be driving in a circular path, but like if you're in a car, your speedometer would always say 10.8, and it's the tangential speed in this circle, and we got to assume that the speed is constant. Assume constant speed. Not sped. Spelling is clearly not my strong suit, but you know, we don't need to spell. That's why I like math, because we only write one letter at a time. Okay, so the equation that we'd like to use here to relate relationship between angular and tangential velocity is this: r omega equals v. This is the radius. This is angular velocity. It's not a w, it's omega. That is very important. If you call that a w, you take the L. That's not a w, that's omega. This is the angular velocity. And this is linear velocity, or tangential speed. Tangential velocity. Okay, so if we want to convert this to angular velocity, because angular velocity, this is in radians per second, well, we would just do omega equals linear velocity, divided by radius. Now we got 10.8 meters. Meters per second. And radius, well, they didn't tell us. So we would need to be given a radius value to be able to solve for angular velocity. Or if we wanted to, we could also solve for radius given our angular velocities. We would just have tangential divided by angular. This would be our radius if we wanted to solve that. But yeah, it's gonna be impossible to solve this question because we need two of the three components here: radius, angular velocity, tangential velocity. We need two of those three to be able to solve for the other. If we're only given one, well, you know, we're gonna somehow need to get that other information somehow. But given that the question is only one sentence long, unfortunately, the best answer that we can have is that it's radius dependent. Okay, so yeah, the above solution is good, considering the fact that the question is a little incomplete. Okay, cool. Okay, now unfortunately I am like, oh geez, I'm on my time limit, so I will have to wrap this up. Let me change over to my camera real fast. Okay, so unfortunately those are all the questions that we have time for today. If you enjoyed today's Q&A and would like to be notified of when we do this next, please hit the subscribe button and ring the notification bell below. If you're interested in submitting your own questions, we have links in the description where you can find the proper resources to do that. Remember to leave a like and a comment, and if you really like the video, share it with your friends. This has been Millan with OneClass, and I hope to see you again soon. Take care, have a great day, and don't forget, physics is always a fun time. Anyone says that physics isn't fun? Nonsense, they're lying. Don't listen to him. Have a great day. Physics, fun.